Hello, welcome back to the 10th week of the Jerusalem Science Contest. Today we're going to be looking at chapters 10 and chapter 11, and these are nuclear medicine is chapter 10, and chapter 11 is a combination of radiation therapy and food irradiation. These are both relatively short chapters, and I think we'll finish probably within about an hour or so. Okay, so we know that from previous things that we've discussed that there are a lot of different radionuclides that we can obtain by fissioning uranium-235. And many of these are useful in nuclear medicine. So you can see there's a list of reactions that produce things such as molybdenum-99 and iodine-131, which are both very useful imaging agents, xenon-133, and cesium-137, rubidium-97. All of these different isotopes, strontium-100, all of these things can be made using uranium-235 as a target and fissioning this in a reactor. But there are some problems associated with that because you have to fish out the particular isotope that you happen to be interested in. There are other kinds of things that you can do. For instance, you can look at an isotope that you might be able to obtain in some other way that might actually decay to the isotope that you're interested in. And there's a number of examples of that. For instance, chromium-50 can pick up a neutron, go to chromium-51, and that gives up gamma ray, or niobium-99. Just spontaneously beta decays to molybdenum-99. So these are examples of that kind of thing. Furthermore, you could also take something like oxygen-18 and bombard it with protons, and you can get fluorine-19 out of that. And again, that's another isotope that is used quite a bit in diagnostic, at least in the diagnostic area of nuclear medicine. So we have all these different techniques, and which one we use is really going to depend pretty much on specifically on what isotope we're actually trying to prepare. And we have to also be cognizant of things like how long the radioisotope is going to last, because if we have to make it off-site and then it has to be shipped to the facility where it's going to be used, obviously there's a delay that's associated with that, and we have to take that into consideration as well. So a good example of what I'm talking about is actually the production of a radioisotope, technetium-99, which we've seen before. And technetium-99 is actually prepared from molybdenum. We can actually make the metastable technetium-99 from molybdenum, which is 4299, and we can irradiate this with a neutron. So we have neutrons, and that's going to go to, I'm sorry, that's molybdenum-98. We want to make that actually, let me correct this. So molybdenum-90, we take molybdenum-98 and we irradiate that with a neutron. That will give us molybdenum-99. So we start out with molybdenum-98, and then we add neutron to that. Captures a thermal neutron, and it goes to molybdenum-99. And then once we've got our molybdenum-99, that's going to undergo beta decay, and that will decay to technetium-99, the metastable isotope, and then that will ultimately decay to technetium-99. So this gives off gamma. This goes off beta. There's probably some gamma produced there as well. This has a half-life of about approximately 2 3/4 days. I think that's about 66 hours. This material has a much shorter half-life. It's on the order of something on the order of I think about 6 hours. It's just a few hours anyway. Let's say 6 hours. I might be wrong about that, but you can find that in your text. And this has a very long half-life. The half-life here is greater than 2 times 10 to the 5th years. So we're talking about a half-life on the order of, this would be on the order of 200,000 years. It's something like 225 or 215,000. And again, I don't remember the exact number. But the point is that this material is very, very useful because it is a gamma emitter, and it's got a relatively short half-life, which means it doesn't stay in the body for a long period of time. If we make this, what we can do is we can actually have this shipped to us, or we can make this, and it's put into something that's called a cal. And it's basically it's a lead-lined device that has there's a column in here. It contains something like aluminum oxide, alumina, which is a very, very good way to actually separate these products. And the molybdenum 99 is actually adsorbed onto the column. So you've got a molybdenum 99 on the column, and you've got up here an injection port, and then there's another port over here where you can receive material that's been eluted or actually washed off of the column. So in here I can take a syringe, and I can actually, with a plunger, and I can actually plunge into here a solution, what we call an eluent, which is the material that's actually going to move this off of the column. So I take my eluent, put it down the column here, and what's going to happen is it's going to wash. The technetium and the molybdenum are on there in the form of, initially we put the molybdate on there, the 99 molybdate, so it's in this oxidation state. It has a charge of 2 minus, so that could be in the form of a potassium or sodium salt, for instance. That would be put on there. And then that decays. When it decays, it winds up decaying to this, which is called, this is molybdate, M-O-L-Y-B, molybdate, and the other one is pertechnetate, and this is the pertechnetate ion. It has a charge of -1. It turns out that the more highly charged material will adhere more tightly to the column. So while molybdate is being converted to pertechnetate, we can actually wash the pertechnetate off of the column just by plunging this with a saline, a salt solution. And then over here we can take a syringe and we can actually collect the radioactive pertechnetate that is being washed off of the column. And what's neat about this, these things are called molybdenum, or sometimes molybdenum technetium cals. And this process that I'm describing is known as milking the cal. So we milk the cal by putting the eluent down through the column and then pulling up on this, and we can get out what we're interested in. And we can do this a number of times. After this thing will eventually reach an equilibrium state where we won't be able to get any more material off of it. But if we actually start washing, there's actually a chart in here on page 183 in your textbook, and it shows the time and days where molybdenum 99 as the parent isotope and technetium 99 metastable as the daughter. And we start out with a high activity of molybdenum 99, and it starts to fall off with time. But each time we do this, we start out with no activity of, basically when we first get this thing, very, very little activity of, this is activity along here, and this would be time on the x-axis. So, I don't know whether you can see this or not. I may have to move this down a little bit. Let me try to readjust my focus, because I may be a little bit too low here to see this. Let's see, am I still on here? Okay, so basically what happens is the activity will go up, then we'll milk the cal, and of course the activity goes way down again, and then we milk the cal, let's say a day later, this is after 1 day, the activity is built back up, the technetium activity is built back up again, and we milk it again. And we can do this 4 or 5, maybe even as many as 6 times with the same cow. And after that, we're eventually going to get to a point where we're not going to be able to get any more activity. After we've milked it greater than 7 daughter half-lives, then we'll reach transient equilibrium. When we finally reach, we'll get to the point where we're really not going to be getting any more useful material out of it. But you can do this for a number of patients. You could schedule this so you could have 6 or 7 patients who would all be able to use technetium that actually came from the same cow. So that's a really good way of actually getting the radioactive material into a patient at the time that it's actually required. Now, in terms of technetium, technetium is one of these kinds of things that actually, depending on what oxidation state it's in, it may go to specific organs. There's one particular compound that's described in your book, which is kind of interesting. And that's if we start out with a pertechnetate, but then we have to actually do something to it to change its chemistry a little bit. So we have the TCO4 minus, and if we treat that with a particular chemical compound, we can make something that's called cardiolite. In your book, it's referred to as 99M technetium sestamibide. Sestamibide. So it's 99M technetium sestamibide. And this, as I said, goes by the name cardiolite. And it is a myocardial perfusion agent. So it's something that basically, it turns out that once we make this compound, which we have to do by reducing this, getting it to a lower oxidation state, we put in something called stannous chloride, tin 2 chloride. The tin 2 chloride winds up being oxidized to tin 4 chloride or stannic chloride. And then we have what is known as a ligand, which is something that actually binds to the technetium. We're going to take the technetium and reduce it down to the point where there's not any oxygens on it anymore. And then we can bind to the technetium 6 of these ligands. And the particular ligand that we're going to put on there is a chemical that has this structure. It's not really shown in your book, although they do give you the name of it. But it's basically what it is a, I'm going to just draw it out for you so you can see. So this group here is called a methoxy group. It's a carbon, 3 hydrogens, and an oxygen. Carbon always has 4 bonds to it. The way I've drawn this, actually, for those of you that have not seen any organic chemistry, I should really draw it probably like this so you can see. When I write out CH3, what I'm really referring to is this. It's a carbon that still has the 4 bonds, 1 to each hydrogen. Hydrogen always has 1 bond, oxygen has 2. So we have this CH3 with an oxygen, which is called a methoxy group. So this is methoxy. This particular group here is called isobutyl. By the way, that's how it gets its name. This is the MIBI part of this is methoxy, is the M, and then isobutyl, the IB, and then this is attached to this, which is called an isonitrile or isocyanide, and that looks like that. So each one of these groups is a ligand, and there are 6 of them, and they bind to this central technetium atom. And then the technetium now is going to have a charge. Before, when it was pertechnetate, it had a charge of -1. Now its charge is going to be +1. After we put these 6, well, the technetium itself actually had a charge since the whole ion is -1, the technetium was actually +7. So once we put these negatively charged functional groups on here, we put 6 of them. This brings us down to a charge of -1, +1, I'm sorry, when we actually put all 6 of those on there. So this turns out that this entire thing, since it's got a plus charge, the body kind of recognizes it or sees it almost as if it were a potassium ion, another singly charged ion. And that will very, very readily perfuse or actually be absorbed into cells in the myocardium, which is the heart muscle. And this is a really good way to visualize the heart, because then these things will be emitting gamma rays, and you can use a gamma camera and get a very good view of the heart as it's actually beating. The other thing that you can do not with technetium necessarily, but with other kinds of radionuclides that can be also used for these diagnostic purposes is you can take them and you can, for instance, this is also shown in your book, you can take certain kinds of materials which are known as chelating agents. And the word chelate actually comes from the Latin. What you in biology you have what are known as chelae, which are actually the claws of a crab. And these molecules, such as the one that's shown on page 187, which is diethylene triamine pentaacetate. So we have a diethylene triamine, which looks like this. Up. Just fix this structure there for a second. 1, 2, 1, 2. Okay, and then you've got another amine here, and then you have these CO2 H groups on here, which are carboxylic acids. These are called carboxylic acids. And there are a total of 5 of these groups. This, by the way, when I draw this, this represents a CH2. So it's a shorthand way of writing that. So we've got a CH2, CH2, nitrogen, CH2. This group, the CH2CO2H, is an acetate group. So 1, 2, 3, 4, 5 is pentaacetate. Each one of these can fold around an ion, such as an indium ion. And you see this actually on page indium 3+ actually forms a complex with this. And then the complex, which I'm not going to draw, which has a 2- charge, can actually then react with some biological molecule and can form through here, we can form what's called an amide bond. This COOH can actually, and this is very much like what happens in peptides, in proteins, you form these CONH groups. So the COOH can lose an OH, and then an amino acid at the end of some protein or a peptide can actually complex with this thing, and then you'll have attached to this something with the radioactive indium one here. And that again can be used as a kind of imaging agent, because the biological molecule will be incorporated into the body, and hopefully it will go to a specific site in the body. You don't. The idea is to have these things not just go anywhere, but to go to specific sites. So the chelae or the claws, these groups actually will grab a hold of that ion, and so they're called chelating agents. CHELATING, or and that particular group is called a chelating ligand. So that's another technique that we can use. We can also do some interesting things if we take specific radioisotopes that will actually emit positrons. So we can use things like fluorine 18, which is a positron emitter, and we can take something like glucose, which is a 6-membered ring that has an oxygen in it. This ring is called pyran, and there's another way to write it, which I'm going to show you. It's the way that it's actually written in your book, and it's still the same 6-membered ring, but you'll see that you have 1, 2, 3, 4, 5, 6, 5 carbon atoms and an oxygen. But this is kind of a three-dimensional or a projection of how the molecule actually looks. So this is glucose, a very, very common biomolecule, something that we need, that we derive energy from, something that is present just about everywhere in the body. And we can take this molecule, this glucose molecule, and it's fairly easy to do some chemistry on it where we can actually replace this OH group. This is called, once we take this OH off of here and we put a hydrogen back on, then it's called 2-deoxyglucose. So what we're going to do is we're going to take a 2-deoxyglucose, but we're going to take the OH group off, and we're actually, instead of a hydrogen, we're going to put a fluorine on there. And then we have the 2-deoxyglucose. So this particular molecule, if we label it with fluorine 18, is a very good positron emitter. And the nice thing about positron emission, you'll remember, is that positrons don't have to travel very, very far before they encounter, they're going to encounter an electron. And once they do, there's going to be an annihilation process that's going to take place. So we're going to get these 2 gamma photons. If memory serves me correctly, they have energies of around 512 MeVs each. And once the positron and the electron actually collide with one another, there's going to be 2 photons produced. One of them is going to be directed this way, and the other one's going to be 180 degrees in the opposite direction. And we can use, again, we can have these photons, these dual photons that are emitted in a variety of different orientations that will give us a 3D image. So if we can get the fluoroglucose to go to a specific site in the body, we can actually image that using, again, a gamma camera. And this process is known as positron emission tomography. We've looked at it before. You can also do, there's also what are known as fusion technologies. And fusion doesn't have the same meaning that it did when we talked about fusing 2 nuclei together, but it means we're fusing actually 2 different technologies. So in this case, we're going to use something like magnetic resonance imaging along with the computed tomography, like positron emission tomography. We can get one piece of information from that. The other thing is we can use MRI, magnetic resonance imaging, which actually uses nuclear magnetic resonance to actually look at water that is in water that's actually in tissues of the body. And it's possible using this technology to actually get an image, another image, and we can sort of superimpose both of these images together. We can get much more information using a PET and CT and a PET scan simultaneously. So there's, a PET CT and an MRI scan simultaneously, so we can get a lot more information from that. So there are a number of these different kinds of materials that we can use, and I've just given you a few of them. The last section in this book talks about radiopharmaceuticals being known as radiotracers. The idea being that we can actually have these kinds of things go to specific areas within the body or within a let me just erase this here. Within an organ, and we'll get a very, very good image of that organ, and we can. It's not a very invasive procedure when we do it this way. It doesn't require surgery, and it gives us a much more complete image than we would get just from simply taking an X-ray or doing any one of these other things, such as MRI. We're getting additional information in this fashion.